Okay, so let's see. Indiscernible. Okay, much better. Okay, very good. Now we'll say it's an indiscernible sequence over A, where A will be a set of parameters, if whenever I0 is less than dot 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 is less than I n minus 1 and J0 is less than dot 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 J n minus 1, we have that the tuple AI0 AI n minus 1 has the same type over A as A J0 A J n minus 1. All right, so a few comments are in order here. So this notation is notation that I'll use all over the place. And what it really means is that the type of A I0 through AI n minus 1 over A is the same as the type of A J0 through A J n minus 1 over A. And by abuse of notation, we'll just simplify this to this. And as the arguments get more involved, this will become clear why this is a useful reduction in the complexity of the notation. All right, so we have lots of examples. Let's consider one of them. So this is an example that I like. So let's consider the following language. So the language will consist of E, which is just a binary relation, and T will be the theory of an equivalence relation with infinitely many classes, all of which are infinite. Okay, so if we pick an element here, let's call it A, we can ask the question, what are the indiscernible sequences that begin with A? And up to isomorphism, up to automorphism of the structure, there are exactly 3 that we can pick, starting with A. And they're very different in character. So the first one is the trivial one. So we could just say AI equals A for all I. This is the constant sequence. Now, of course, the constant sequence is trivial because no matter how many indices I take, sorry, the constant sequence is of course indiscernible because no matter which n-tuple of indices I take, the things are all just going to be A. So of course, if I have an n-tuple which has A, that's going to have the same type as any other n-tuple which says A, and this is not a very interesting indiscernible sequence. Okay, now the second one that you could pick is one like this, which stays in a class. So this one is axiomatized by saying AI is different than AJ for I not equal to J, but they're equivalent. So this one stays inside a class. And then notice that there's a third one, which goes like this. So this one is axiomatized by saying it's not the case that AI and AJ hold when I is different than J. So these are the 3 possibilities. And what you'll notice is that if you're an indiscernible sequence, then if you take a pair, then you have to be able to decide whether or not an arbitrary pair is equivalent or not. And if it's indiscernible, then you always have to get the same answer. If you take any distinct pair of elements from your sequence, they have to be either equivalent or not. And so these are the only 3. You get a uniform answer everywhere in the sequence. Either they're all equivalent or they're all not equivalent. Okay, so this is a kind of example of an indiscernible sequence. A non-example is take the following structure of the integers with the successor relation. So S of x is interpreted to be x plus 1. All right, and now consider the following sequence. Define AI to be I for all I in the natural numbers. So this is a sequence. And one thing that you can note is that AI has the same type, not over A, over the empty set, as AJ for all I and j less than omega. So here you have a sequence, and there's an automorphism that takes any element of the integers to any other element. So if I look at the integers, here's 0, and here's some number k, I get an automorphism of the structure by sending 0 to k, and then shifting everything else up by k. And because all the formulas are preserved by the automorphism, that tells you that any element of the integers will have the same type over the empty set as any other element of the integers because they're conjugate by an automorphism. So why is it the case that this sequence does not define a indiscernible sequence? Well, the problem is that if you look at A0 and A1, this pair will satisfy the formula that says S of x is equal to y. Because 1 is the successor of 0. But if you look at A0 and A2, that says that S of x is not equal to the successor of y. And these are different. So you found a formula that distinguishes them, and that means that they can't be the same. Okay, cool. So hopefully this is a notion which is familiar to most of you. Now, oftentimes in model theory, we don't just want to produce indiscernible sequences, but we want to produce indiscernible sequences which somehow closely resemble a given sequence of tuples, which is maybe not indiscernible. We want to find an indiscernible version of it. And there are various different ways of formalizing this notion, but one that we'll use is the notion of an EM type. So here's the definition. So suppose AI, I in omega, let's say, is a sequence of tuples of the same length. And A is a set of parameters. Then the EM type, let's call this I, just for simplicity. The EM type of I over A is the set of all LA formulas. So this notation means that it's the formulas in the language that have parameters coming from A. Phi x0 up through xn for any n, such that for all, and here this universal quantifier is important, for all I0 less than dot 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 less than I in minus 1, sorry, this should be in minus 1, in omega, we have that A I0 dot 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 A I in minus 1 is true. All right, so let's go back to our previous example. So for this one, we'll need to know something about the structure, but remember we were in ZS, and we had a sequence which was AI, I less than omega, defined by AI is just equal to I. Okay, now the question that we want to ask is, what is the EM type of this sequence? So let's call this I. So what is the EM type of I over the empty set? All right, so what is it that the formulas can say in this language? So you have quantifier elimination in this language. And so the only thing that you have in the language really is equalities between terms. So for example, we don't need to axiomatize the entire type, but let's just say it contains, for example, x0 is not equal to x1. Because, no element of the sequence is equal to any other of the other elements of the sequence. But for example, can we say something like S of x is equal to y? That's satisfied by one of the pairs, namely 0 and 1, or 1 and 2, or 2 and 3. So this is in the EM type. An empty set. But this one is not in it. Why? Well, because it's satisfied by one of the pairs, in fact, infinitely many of the pairs, but not by all of them. So this is something which is not sort of universally true for pairs of increasing tuples. And then the pair like s squared x equals y, s cubed x equals y is also not going to be in the EM type. So this is just the stuff which is true somehow, no matter where you look inside the sequence. And so the idea that we're going to have for what does it mean to have an indiscernible sequence that resembles a given sequence is we want to find an indiscernible sequence that realizes the EM type of the given sequence. And notice that somehow that's like, well, it's interesting to ask what would happen if I computed the EM type of an indiscernible sequence. So I took the indiscernible sequence, like let's suppose I was not just a set of tuples of the same length, but it was actually an indiscernible sequence. Then what happens when I take the EM type? In this case, I get a complete type, actually, because every formula, if it's true somewhere, then it's true everywhere. So this all becomes a sum. I mean, it's equivalent. I can switch the for all to a sum, and I make a decision about every formula. But if I have a sequence which is not indiscernible, then there are going to be two increasing in tuples and some formula where they disagree. And that means that the EM type won't be complete. So in fact, the EM type is complete if and only if the sequence is indiscernible over the set A. All right, so now what we want to do is we want to prove the following theorem, which says, suppose I equals AI, I less than omega, is a sequence of tuples of the same length. And A is a set of parameters. Then there is an A indiscernible, or A indiscernible means the same thing as indiscernible over A, sequence J, that realizes the EM type of I over A. So this is another abusive notation. Normally the symbol means, of course, satisfies, and it's the relation between a model and a formula, or a model and a theory. But here we're going to use it to mean that you can take a tuple or a sequence and use the symbol to mean that it realizes a certain partial type. So this means realizes. We'll use this a lot too. All right. Now, we won't finish the discussion of this theorem, but there are going to be sort of two routes to the proof. Okay, and both of these are going to be really meaningful in the subsequent discussion of the class. So one of the ways of, oh, sorry, I got rid of this before I should have really. So one of them is Ramsey theory. And this is probably the argument that most of you saw in arguments about why indiscernible sequences exist. You can describe a certain compactness argument, which uses Ramsey's theorem, and And then from this compactness argument, you produce an indiscernible sequence. And we'll do that. Then there's another argument, which probably you haven't seen, which uses something called average types or invariant types. And spiritually, this is very close to Ramsey theory, but in model theory, somehow the setup here using average types or invariant types has uses which go well beyond just producing indiscernible sequences. It'll produce indiscernible sequences with particular model-theoretic properties, which will be very useful going on into, especially into NSOP1 and TP2, so on and so forth. So we're going to give both of these arguments. And the reason that I want to do this sort of slowly, and we'll start today and then finish on Monday, is that I think both of these aspects reflect really important sides of the theory of model-theoretic tree properties. So in Ramsey theory, we start with just Ramsey's theorem, but then this gets generalized to Ramsey structures, Ramsey classes of structures. And this gives us a way of producing generalized indiscernibles. And we're going to prove a theorem of Lin-Scow, which says that, in fact, generalized indiscernibles are somehow equivalent to Ramsey classes of finite structures, which is combinatorially interesting. And then also this stuff about average types will play a role in sort of our understanding of dependence, sort of like what does it mean to look at dependence at a generic scale? What does it mean to have indiscernible sequences that somehow fill space? And average and invariant types will be the main tool there. So both of these things, you know, it seems silly to give two proofs of a theorem that you all know, but I want to do that just because I think it's a nice way of seeing the tools. All right, so let's start with this one. And then this one we'll do next time. Now, let's just recall some notation. So suppose I have some numbers, like let's say in, k, r, and in, which are less than omega. And we're going to write the following symbol, which is the Erdos-Rado arrow notation. Oh, wait, no, I did it wrong. I always do it wrong. Okay, the number in goes to parentheses in superscript k subscript r. Okay, so what the hell does this mean? This means if f is a function from capital N to k, and okay, now I have to say what this means. This is the k element subsets of the set 0 through n minus 1. And this function is like a coloring with R colors. So I take my capital N element set, I look at all of its K element subsets, and I assign them R colors. So suppose I'm in this situation. Then, so if, then there is some X, which is a subset of this capital N element set, which is not too small. So the size of X is little n. And it has the property that all of the K element subsets get the same color. So if I look at F and I restrict it to the K element subsets of X, this is constant. Okay, so I should have tried to fit it on one screen so everyone would get it, but okay. This is the notation, and this is what it means. It means the statement. Whenever I have a coloring, I can find a homogeneous set, and the specific parameters say that whenever I have a coloring of a really big set, capital N sized, I can find a homogeneous subset of little n size. Okay. Now, there's no reason to restrict this to natural numbers. So we can also give the infinitary version. So omega arrows omega k r means exactly the same thing. So it says if f is a coloring which goes from k element subsets of omega to some r element set, then there exists some x subset of omega which is countably infinite. I mean, every subset of omegas at most countably infinite, such that if I restrict f to the k element subsets of x, then that's constant. All right, so this is familiar. And what Ramsey's theorem says is just that these statements are true. So Ramsey's theorem just says two things. So we have the finite version. Let me move down. So we have the finite version. And this says for every choice of our little numbers, n, k, and r, there exists some capital N such that capital N arrows n, k, r. So this says if I want to be able to find a homogeneous set of size little n, then I have to choose the domain of my coloring to be a set of size capital N. But as long as I make it really big and make it capital N size, I can be guaranteed to find a homogeneous set of size little n. Okay. And then the infinitary version is nicer because it has fewer quantifiers. So the infinite version is just that omega arrows omega kr. So whenever you color the natural numbers with the k element subsets of the natural numbers with finite many colors, you can find an infinite set, which is homogeneous for that coloring. And homogeneous, sorry, I should have said this. Homogeneous means that whenever you color the k element subsets, you get the same color, no matter how you do it. It's exactly the same statement as saying that if I restrict the function to the k element subsets of that set, then it's constant. So homogeneous for the set means that the function is constant on the k element subsets. All right, so we need to put this to use. And so let's just prove the theorem. So here, let's go back to what the theorem said. Okay, so we will copy. And now we will paste, but make it small. Oh no, I wanted to make it small. Well, I guess I'm making everything small. That's fine. All right, so let's prove this, but we're going to use Ramsey's theorem. And then that'll be it for today. All right, so what we'll do is we will let gamma, which is going to be a partial type in the variables xi, I less than omega, be the partial type, the set of formulas. So I take the union of the EM type of I over A and the following assertions. So I just look at for all n, I just say phi x I bar if and only if phi x j bar, where phi ranges over all LA formulas. I bar and j bar are increasing in tuples from omega. And let me just clarify my notation, where x I bar is just shorthand for x I0 dot 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 x I in minus 1 when I bar is equal to I0 through I in minus 1. Okay, so if I take an increasing in tuple, I can just look at x sub I bar, and that's going to be the in tuple of variables with the corresponding indices. Now, the thing to observe is that if gamma is consistent and J realizes gamma, then J is the indiscernible sequence we're looking for. Why? Well, for one thing, gamma includes the EM type. So of course, if I realize gamma, then I automatically satisfy the correct EM type. So the only other thing that we need is for J to be an indiscernible sequence. What does it mean to be an indiscernible sequence? It means that no matter which in tuple I take, I get the same type. Now, but what does it mean to have the same type? Well, to have the same type means that whichever formula is true here needs to be true here. So if you unravel what all that means, it's exactly that I satisfy this type. It says no matter which increasing in tuple I pick, the formula on the increasing in tuple I bar will be the same as the formula on the increasing in tuple J bar. The truth value doesn't change. Okay, so what do we need to do? We need to show that J is consistent. And in model theory, how do you show that something is consistent? Well, you use the compactness theorem and you consider a finite subset. So we'll use compactness. Now, let n be less than omega and delta be a finite set of LA formulas in free variables. So what we'll do is we will use Ramsey's theorem. So we need to cook up a certain coloring. So what we'll do is we will define F, which goes from in element subsets of omega to a finite set of colors. And what is the finite set of colors that we'll take? Well, what we'll choose it to be is just the power set of delta. So that's not a number. It's not the set 0 through r minus 1, but of course it's in bijection with a finite set like that. And because delta was finite, the power set of delta is also finite. So this is certainly finitely many colors. And so Ramsey's theorem tells us that anytime we have such a coloring, we will be able to get a homogeneous subset. So what's the coloring we want? Well, what we'll do is we will look at f of I0 through I in minus 1. Assume these are written in increasing order. This should just be the formulas phi in delta such that phi a I0 through phi a in minus 1 is true. So, you know, if I take an in tuple from my sequence, I can just ask for each formula in delta, are you true or are you false? And the subset of delta consisting of the true ones will be the color that this in tuple takes. Now, what does it mean for something to be homogeneous with respect to this coloring? It means that no matter which in tuple I take, I get the same answer for each formula in delta. I either get true, 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 or I get false, 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 false for each in tuple, although of course the truth value between the formulas can change. And so by Ramsey's theorem, there is some x infinite contained in omega, such that f restricted to the intuples from x is constant. Then I can look at the restriction of ai I in x. Now, let's remember the way that EM type was satisfied or defined. The way the EM type was defined said that if I take an intuple from anywhere in the sequence, then the formula has to be true. Now, if I restrict to a subsequence, then that's still the case, right? If I take an intuple from a subsequence, then it's an intuple from the big sequence. If a formula was true on every intuple from the big sequence, then it has to be true on every intuple from the small sequence. So this thing will certainly still satisfy the EM type of I over A. But by the choice of X, we have phi A I bar, if and only if phi A J bar, for all phi in delta, and I bar J bar increasing in tuples from X. Now, this is the union of the EM type together with sets of this form. These contain, sets of this form contain every finite subset of gamma. So if you take an arbitrary finite subset of gamma, it will consist of some finite piece of the EM type, and then there will be some finite set of formulas and some biconditionals involving that finite set of formulas, and some finite number of variables. So if I include all of the variables and I include all of the EM type, and I just restrict the number of formulas to some finite number, then sets of that form will certainly contain every finite subset of gamma. And I found realizations for all of these sets, and that means that I found realizations for every finite subset of gamma. So by compactness.
I'm sorry, hold on a second. How do we know
Is there a question?
X's were, yeah, so how do we know that the X's were guaranteed from Ramsey's theorem? Don't like all of one.
Sorry, I'm having I can't quite hear you. It's very quiet.
In order to show that every finite subset of gamma gets covered by this process, we need to get every possible value of I bar and J bar. How do we know that all the X's we get from Ramsey's theorem don't avoid some particular I bar?
So the point is that X can be enumerated in order type omega. So here when I say increasing intuples from X, I mean what I could really do is I could think about X as being like I could list its elements as, I don't know, let's say A, I, K, as K ranges over the natural numbers, where I, K is going to be less than I, K plus 1. So I've listed it in increasing order. And then what I'm doing is I'm imagining assigning A, I, K to the variable K. Like the kth element in my sequence realizes the variable K. So I realize all of the variables. And so so there's no part of the biconditional that I'm missing. I've realized every part of the biconditional. Is that clear? So my point is, if I do this, then this realizes what does it realize? It realizes the EM type of I over A and phi x I bar, if and only if phi x J bar, as phi ranges over delta, and I bar and J bar are increasing in tuples, not from X, but from omega. And certainly every finite subset of gamma is contained in the set of that form.
I see.
Okay.
Thank
Okay, cool. Okay, so that's the proof, which is great because we're definitely out of time. All right, so next time we'll give a different proof using a different kind of model-theoretic technology. We'll start with invariant, finitely satisfiable types, and then we'll move very swiftly on to generalized indiscernibles. But thank you all for coming. I'm very excited about this class, and it's really nice to see so many people here. And yeah, be in touch about anything related to the course, and we will try to figure it out together. Cool. Okay, so that's it. Thanks.